how to keep them running for a long amount of time. Because if we're going to invest a lot of taxpayer dollars in this, we want this thing to last a long time so we get a great science return from the mission. We also are looking at James Webb. We might have something that looks a lot like James Webb when we do this mission, and we might have something that looks bigger, but either way, if we want to go big in space, we have to fit it inside a rocket, and the only way you do that is if you have a segmented mirror instead of what's called a monolithic, a single spherical mirror, which is what Hubble had. James Webb has all these panels, and it has that, so those panels, this is too big to fit inside the rocket, this might fit inside the rocket. So Webb goes up like this, and it unfolds, and that architecture for the paneled mirrors, for the mechanics of how the transformer telescope unfolds once it gets outside the rocket, all that's being developed by Webb. It's launching later this decade. That feeds into this. We also have a mission that's going to start after Webb launches. We're going to start developing and building this mission called WFIRST, which has a mirror very similar to Hubble. It has technology development that they're considering to do the starlight suppression part of it, which is, I think, one of the major technical challenges. So between WFIRST and JWST, we'll know how to do the starlight suppression, we'll know how to build big telescopes, and from Hubble and JWST and WFIRST, we'll know how to operate them in space. We also have these missions, Kepler, which is where the data I showed you earlier comes from, and TESS, which is going to launch in a couple of years, that are telling us about the universe of exoplanets that are out there, so we understand what kinds of things we might be looking for. So if we put all that stuff together, and the brilliant engineers at Goddard and JPL, and really in academia and in industry, if they all come together and they continue this technological progress, we can end up with something beautiful like this. Donald Trump would say this is big and it's beautiful. Okay? It's a huge telescope in space that would get us some wonderful data. So that gets us this pale blue dot, okay? And this is the image that sort of started the pale blue dot phrase. This is Carl Sagan's pale blue dot, where they took an image from the outer solar system looking back at Earth, and he had this poetry, right? He said, everything that's ever happened on Earth, all our wars, all our triumphs, all our troubles, all of history of humanity has happened on that one speck of light in the night sky, right? So it's really poetic. But as a scientist, it's like, okay, but you're asking me to tell you whether or not that one speck has life or not, right? That's a tough problem. So how do we do that? We do that by literally making a rainbow out of it. We want to find out essentially how blue it is. We take that one speck of light and we split it up and do a spectrum. We actually send it through something that's kind of like a prism, split it up into a spectrum of colors, and then we look for the absence of certain colors in that spectrum. And we look for the absence of certain colors because certain gases absorb or block out certain wavelengths, certain colors of light. And the absence of those colors tells us that there is that gas in the atmosphere. Carbon dioxide has its own features, which is why it's a greenhouse gas. It traps the colors that Earth is emitting out, and it absorbs those and reflects that radiation back to space. That's what the greenhouse effect is all about. Water does it too, and it actually amplifies what the CO2 is doing. So does methane. At other wavelengths, we have oxygen and ozone absorbing light that comes from the sun. And oxygen and ozone are gas. Well, oxygen is made by light, and ozone is a byproduct of oxygen being in the atmosphere. And the story that we are building this telescope around, or telescopes like this around, is that if we see oxygen or ozone on a planet around another star, we have detected essentially forests and cyanobacteria and algae, basically, the things on Earth that make oxygen when they do photosynthesis. But there's something I worry about. I don't really have nightmares, but if I did, this would be like what would go through my head. I probably do. I'm probably just not like, I'm a 2-year-old, so I'm probably just not like remembering what my dreams were. But this is what would keep me up at night if it weren't for a crummy kid keeping me up at night. It'd be this image. So this is, does anyone recognize this?
Allen Hills.
Allen Hills. So this is, in some ways, we can already declare success, right? So 20 years ago, when I was having that conversation with my brother, NASA was already announcing that it had found evidence of life on another planet. This is a meteorite that had been ejected off the surface of Mars, traveled through interplanetary space, landed in Antarctica, was then uncovered by scientists, brought into their lab, and they did a number of tests on that meteorite. What they found was this little critter, or what they call a nano. This is something that looks a lot like a microbe. It looks like life, doesn't it? And they also found some other evidence that they claimed was evidence of life. Fast forward 20 years to today, I think this is how I feel, and I think if you polled the astrobiology community broadly, they would say, yeah, all the things that they said were evidence of life surely are things that life could have done. However, there are also non-biological processes that could explain all of the data from that paper. And furthermore, this thing is smaller than known Earth organisms. In fact, it's so small, it's at the theoretical limit of how small an organism could be, given our knowledge of all of the information that's needed to put inside a cell for genetic history or for genetic information, and also the building of proteins and cellular structures and all that. So in other words, we have another process or another set of processes that can explain all the data, and we've got some theoretical reasons to question whether or not this is life in the first place. Okay, and this isn't the first time this has happened. If you go further back in time, and you go back to the Viking lander, there's a guy named Gil Levin who had an instrument called the labeled release experiment on the Viking lander on Mars. So they set foot down on Mars, scooped up some soil, tossed it into its back, had some ovens and other things to analyze the soils with. And there were 3 tests for life or for signs of habitability, and this one came back positive. The hypothesis was if you basically inoculated this soil with radioactive labeled carbon, you would see a release of another kind of radioactive carbon in another form if life was processing that carbon, and that's pretty much exactly what they saw. But the other 2 experiments came back negative. Critically, one of the experiments was looking for organic material and found very, very, very little organic material. Which means that if you've got life there, what the heck is it made out of? And the other experiments also suggested that this is not life. Now, if you ask Gil Levin, actually, you don't have to ask Gil Levin because he'll tell you, even without asking, that he was the first person to find evidence of life on another planet. But again, I think most people in the astrobiology community would say he did not. That he found some interesting soil chemistry and some interesting carbon chemistry that was occurring inside the apparatus. And unless you think I'm picking on the Martians, this also has happened in Earth's history. When I was a grad student, it was always fun to read the papers about the earliest evidence of life on Earth, especially the microfossil evidence, because the professors went at each other, right? I mean, it would be like, they weren't swearing in the paper, but you could tell they were swearing when they wrote the responses to the paper, if you know what I mean? So that was fun as a grad student to read all that, and kind of scary. But again, so this is work by Bill Shaw, which at this point was claimed to be sort of the earliest fossil evidence of life on Earth, and this has set up huge controversies, again, because there are non-biological processes that can do a lot of these things. So the take-home point for me, as someone thinking about another experiment that plans to look for life in the universe, is it's actually pretty easy to think of something that life does that you could look for, and then build an instrument to then go and look for that thing that life is doing. What's hard is figuring out all the other processes that could lead to the same signal that have nothing to do with life. Okay, I call them false positives, right? Eliminating the false positives is the hard part. And this is what I've been spending, specifically, my part in this the last 5 years or so has been thinking really hard about that. So I'm not the only one that's been doing it. There's a bunch of us doing it now, and we're coming at it from different perspectives. I'm a chemist, I'm an atmospheric chemist specifically, and I've been thinking a lot about how photochemistry could do this. So if you have carbon dioxide in the atmosphere, and remember it's oxygen and ozone, O2 and O3 are the 2 main gases that we plan to look for life on another planet. I know people have heard of methane, I'll get to that. So photochemistry could do this. If you've got carbon dioxide, which is a carbon and 2 oxygen atoms, you can split off the oxygen atom with a photon and make CO and O. And if you do that enough times, you could, in theory, recombine those O atoms to form O2 and O3. Now, the thing about this is it only happens for environments in which you don't have something else to react with that O. If you form the CO and the O doesn't react with another O, it reacts with something else, then you're not going to get O2 and O3. And in most cases, that's what's going to happen. Okay, so in most cases, what is going to happen is that oxygen is going to find a hydrogen somewhere, react with that, and you're never going to get the O2 and the O3. Atmospheric loss. So these 2 kind of feed into this one, and they're also sort of more exotic versions of it. Around certain star types, for a long period of the history of the star, these are cooler type stars, they're called M dwarfs or M type stars if you're into the classification schemes. They have a long period of violent activity, the star does. And what that does is it imparts a lot of high energy radiation to the planets around the star. Turns out that you can give enough energy to the atmospheres of these planets to drive loss of hydrogen atoms to the top of the atmosphere. Now, if you're losing the hydrogen atoms, there's nothing for the oxygen to be combined with other than itself. I'm simplifying it to some extent, but in broad terms, that's essentially what can happen. And you can build up a planet, in theory, that has up to 90% oxygen without any biology in it, just from a loss of hydrogen and oxygen being left behind. Okay? And then lastly, you can have a planet that doesn't have a cold trap. We have a cold trap on Earth, thankfully. It forms clouds that give us a hydrological cycle. It also prevents water from getting up into the upper atmosphere of the planet. If you don't have the cold trap is basically water gets up to a certain point where it condenses just based on the equilibrium conditions, forms clouds, which eventually grow, the droplets grow heavy enough to form rain, and it pushes the water back down. If you don't do that, the water can go higher and higher and higher. You can get up into the uppermost parts of the atmosphere, and the water can get split by photons into OH plus H, and the hydrogen can escape to space, preferentially leaving behind oxygen. This also, in theory, can build up O2 and O3. And I'm worried about this, even though all of this stuff is only theoretical, because as the person that wants to, that's advocating or talking about building a telescope to look for oxygen or ozone, even if it's just a theoretical way to make oxygen without life, I want to know about it before I build the telescope and launch it into space. Okay? So what's cool about all this is basically about the battle in the atmosphere between oxygen and hydrogen. You hear professors talking about redox chemistry. It's important, right? Like it drives so much of the other chemistry in a system. It's so dependent on the redox conditions. Whether you're talking about mantle chemistry or atmospheric chemistry or aqueous geochemistry or groundwater chemistry, or the incentives from biology to do different metabolisms, redox chemistry is key. And in the context of this atmospheric discussion and the ability of an atmosphere to make oxygen without life, redox is basically the balance, in simplest terms, between oxygen and hydrogen atoms in the atmosphere. And so if you found oxygen or ozone, and you wanted to know that it was from life, you wanted to rule out all of these non-biological mechanisms for making the oxygen or ozone, you'd want to detect hydrogen. And the problem is, hydrogen, H and H2, don't really have many good things that you can detect in the atmosphere. However, methane does. Well, not great, but it has some things you might actually have a chance of seeing. So I'm going to skip over some of these. Are some of the detailed slides on the stuff I just went over. So what we want to do is, the slide I was showing you before was over here. Okay, and if you imagine a planet where we've done the spectrum, we found the oxygen and the ozone, we found water, so we know that we've confirmed that there's potentially liquid water oceans on the planet. Maybe we even see some glint off those oceans and confirm that that water's condensed at the surface. Then we want to know, is that oxygen really made by life, or is it possibly made by a non-biological process? I want to know two extra things about that planet. First of all, I want to know what the heck's going on in that star, because all the processes I just mentioned are contingent upon the star having certain properties. Specifically, a lot of high energy radiation that can either drive the atmospheric chemistry in a certain direction or the atmospheric escape in a certain direction. So the context here is key in terms of the stellar, what the star is doing to the planet. Secondly, I'd want to look for that hydrogen. I told you the hydrogen itself is hard to find, but methane, which has 4 hydrogen atoms, you can detect. The problem is, so we can see it, we can only mostly see it at either longer wavelengths, or we can see it at higher methane concentrations. So this is just some model spectra my student Eddie Spiederman, who's at the University of Washington, did at 0, 0.1, 1, 10, 100, and 1,000 times the modern day levels of methane. So for anything that's 1 times methane or lower, you only see a difference between the yellow and white lines out here and out here. In other words, past 1.5, ideally past 2 microns. So you'd say, okay, Sean, just build a telescope that can see out that far. The problem is, if I want to build a telescope that sees at these long wavelengths, it has to be cold. Because if it's not cold, the telescope itself will be emitting photons at these colors. This is like if you put on IR goggles and you see like, or a heat map. Have you ever done like they do this, actually the better analogy for like 2015 is if you have a home energy assessment, they bring the IR camera into your house and they see where the heat's leaking in to the house or leaking out of it. They're using an IR camera, okay? And so what that lets you do is it lets you see the photons that are emitted by things that are around room temperature or a little bit warmer. Well, if your telescope is room temperature or a little bit warmer, it's going to be emitting those IR photons out here, and it's essentially going to overprint any signal that you'd be seeing from the planet in your camera. So that's bad. And you say, okay, we'll make a colder telescope. Now we're going to do a place where we're talking about money.